Hello, my name is Makena Noone, and for my physics video project, I'll be doing a demonstration of physics in the real world. A great example of physics in the real world actually involves roller coasters that you see at amusement parks. And so the concept that I will be focusing on is the loop-the-loop. And so this classic element of theme park roller coasters is a great example of the physics concept of conservation of energy. The conservation of energy states that the total energy of an isolated system remains constant despite internal changes. So in the loop-the-loop, there are three types of energy at play. There's work, which is the energy transferred to an object by the application of a force over a specific displacement. This is represented by the equation W is equal to F delta X, where W represents the work done in joules, F represents the force, and delta X represents the displacement of the object. Work can also be defined as the change in kinetic energy over time. Another type of energy at play is potential energy. An object can have potential energy by virtue of its surroundings. It's also referred to as stored energy. In this specific case, the type of potential energy used is gravitational potential energy. Gravitational potential energy is represented by the equation PEG is equal to mgy, where m is the mass, g is the gravitational force of acceleration, which is 9.8 meters per second squared, y is the height. The third type of energy at play is kinetic energy. This is the energy of motion. It's the energy the object has due to its motion and is represented by the equation 1/2 mv squared, where m is the mass and v is the velocity. To represent this concept of the loop-the-loop, we are going to be doing an experiment that is very similar to it. We are going to be looking at a paper loop-the-loop and looking at a little ball that rolls through the paper and goes through the same loop that a roller coaster would go through. Through this experiment, we are looking at the minimum height needed for the ball to make it around the loop without falling off. Just some concepts to think about before we go into it. If we look at this loop here and we look at the lower height, little h, and the bigger height, big H, what do we think will happen at each height? When the ball is raised from the table, work is being done on the object. This initial potential energy of the ball is equal to the work being done. And when this height is higher, more work is being done, which means that higher heights correlate to higher values of potential energy. At this height, the kinetic energy is also equal to 0 as the ball is stationary and not released. When the ball is let go, it begins to accumulate a speed. This signifies that the initial potential energy is transformed into kinetic energy, as kinetic energy is the energy of motion. At this final stage, and by final stage, I mean the very top of the loop, this potential energy is 0 as it all has been transformed into kinetic energy and it is completely in motion. At this beginning initial point right here, there is no kinetic energy happening because the ball is stationary. However, there is a lot of initial potential energy because the ball has the potential for movement. Then when it goes up the loop, our final point is going to be right here, right at the top. There is no more potential energy. So knowing all of this, we can determine that the initial potential energy is equal to the final kinetic energy. Looking at the free body diagram of this moment, you can see that the normal force and the force of gravity are both acting down. So in order for the ball to be able to roll smoothly over, the centripetal acceleration needs to be greater than or equal to the force of gravity. Since the initial potential energy is equal to the final kinetic energy, we get this equation here. Doing some algebra, we get v squared is equal to 2gh. Since we know that the minimum value of the centripetal acceleration for the loop to be able to work needs to be equal to the 9.8, we can set up this equation where we substitute in 2gh for v squared. Doing some more algebra, we get the value h is equal to r over 2, where r represents the radius of the loop-the-loop. So the total height would be 4 over 2r since the diameter is 2r, plus 1 over 2r since it needs to be that height above the loop, giving us a total height of 5 over 2r in order for the loop to be successful. These first couple rounds show the ball being released from the lower height. As predicted, the ball was not able to complete the loop and it dropped halfway through. Now we will look at the ball being dropped from the required height. The ball was able to make it all the way through the loop and it was successful. So, what is the purpose of this? The experiment that we just did proves that there is a direct relationship between the potential energy and the kinetic energy. This directly relates to the concept of the roller coaster going around the loop. The roller coaster needs to have enough potential energy so that it can get all the way around the track without falling off. This is why you see a lot of roller coasters having the really big drop before going straight into the loop, and the higher the height, the more potential energy it has, which means the more kinetic energy it has. So that was my demonstration of physics in the real world, and thank you for watching.